Namaskar, friends. Today we will continue our discussion on plastic limit analysis. In plastic limit analysis, our intention is to find out plastic limit load. Plastic limit load is the load that acts in the structure when the structure plastically deforms while acquiring a certain collapse mechanism. It is worth recalling that when a structure collapses, nowhere in the structure moment can exceed plastic moment MP. So there is a limiting moment which exists and remains constant in the hinge, plastic hinge about which the structure deforms. And the maximum value of this moment is MP. So now let us try to understand plastic limit analysis by considering an example which is there in front of our screen. So on our screen, we are seeing a beam which is fixed on the left end and simply supported on the right end. And this beam is experiencing a load of 2P at distance L/4 from left end and a load of capital P at distance L/2 from left end. Let us try to solve this using principle of virtual work. Our first step is to think of a collapse mechanism. Now, let us propose this collapse mechanism wherein there are three plastic hinges. First hinge is on the leftmost end of the beam. Second hinge is at a distance of L/4 from the left end, and the third hinge is at a distance of L/2 from the right end. We can see that beam experiences a rotation of delta theta about first hinge and experiences a rotation of 2 delta theta in the second hinge, which is at a distance of L/4 from the left end, and there is a rotation of delta theta in the third hinge. Now, equating the external and the internal virtual works, we can see that the external virtual work in this particular case is 2P1 into L delta theta by 4. And the internal virtual work is MP delta theta corresponding to the first hinge plus MP2 delta theta corresponding to the second hinge and MP delta theta which is corresponding to the third hinge. From here we can find out capital P1 equal to 8 MP by L and 2P1 equal to 16 MP by L. So we have obtained the values of P1 and capital and 2P1. Now let us draw the free body diagram of the beam. On the left end, there is a plastic moment MP, and the loads are 16 MP by L at distance of L/4 and 8 MP by L at a distance of L/2 from the left end. Let us consider a section at distance x from the left end and write the deflection equation. EI d square v by dx square equal to R1x minus MP minus 16 MP by L bracket start x minus L/4 bracket close minus 8 MP by L bracket start x minus L/2 bracket close. At x equal to L, That means at the rightmost end, moment would be 0. So that gives us 0 equal to R1L minus MP minus 16 MP by L into 3L by 4 minus 8 MP into L by 2L. From here, R1 comes out to be 17 MP by L and R2 comes out to be 7 MP by L. So we have found out the reactions capital R1 and capital R2. Now let us draw the bending moment diagram. So this is a free body diagram of the beam which we were considering, and corresponding to this, let us draw the bending moment diagram. If we draw the bending moment diagram, we find this bending moment diagram wherein at the leftmost end, the bending moment is minus MP, and at a distance of L by 4 from the left end, the bending moment is 13 MP by 4, and at a distance of L by 2 from the right end, the bending moment is 7 by 2 MP. Worth appreciating here that the maximum bending moment here is 7 by 2 MP, that means 3.5 MP. So that means the at distance x equal to L by 2 from left end, bending moment is exceeding the plastic bending moment MP. So that means this particular solution is not the exact solution. That means our choice of collapse mechanism is not the best one. We should be looking for some other collapse mechanism. And this also means that we get an estimate. Now, from this, we can find out the load, the plastic limit load, but that plastic limit load would be overestimated. So the load found would be greater than the plastic limit load. And so here in this case, the P1 is 8 MP by L. So the plastic limit load would be less than 8 MP by L. Now, if we multiply the load P1 by 2 by 7, the figure 2 by 7 is we are getting from here. If we inverse 7 by 2, we get 2 by 7. If we multiply the load by 2 by 7, then we get 16 MP by 7 L. P1 equal to 16 MP by 7 L. So this gives us a range. The lower limit is 16 MP by 7 L, and the upper one is 8 MP by L. Now let us proceed further and propose another collapse mechanism. In this collapse mechanism, we can see that there are two plastic hinges. On the left end, the plastic hinge is experiencing a rotation of 3 delta theta, and at a distance of x equal to L by 4, the plastic hinge is experiencing a angular rotation of 4 delta theta, and the hinge at rightmost end is experiencing a rotation of delta theta. Now, here we have the free body diagram of the beam again, where the vertical reaction at the left end is capital R1 and the vertical reaction at the right end is capital R2. Let us apply the deflection equation on a section which is at a distance of x from the leftmost end. We get EID square V by dx square equal to minus MP plus R1x minus 2P2 bracket start x minus L by 4 bracket close minus P2 bracket start x minus L by 2 bracket close. Now we argue that at x equal to L, the moment has to be 0. That gives us R1 equal to bracket start MP plus 3P2 L by 2 plus P2 L by 2 bracket close into 1 divided by L. So let us call this equation as equation A. And also now let us calculate the external virtual work here. The external virtual work here would be 2p2 into L by 4 3 delta theta plus p2 into L by 2 delta theta. This we can see from here. The external virtual work has to be equal to 2p2 into L by 4 3 delta theta plus p2 into L by 2 delta theta. And the internal virtual work we can see has to be mp into 3 delta theta plus mp into 4 delta theta. So this gives us p2 equal to 7 mp by 12. Substituting in equation A, we get the value of R1 as R1 equal to 8 mp divided by N. And similarly, we can find out R2 as 3p2 minus 8 mp by L, and we get R2 equal to 5 mp by 12. Now, let us try to make the bending moment diagram corresponding to the results which we have just found out for R1, R2, and P2. We can see that for all the points which are in between x equal to 0 and x equal to L by 4, we can write EI d square V by dx square equal to R1x minus MP. And at x equal to L by 4, we can compute the moment, and the moment would come out to be MP. Similarly, for all the points on the beam which lie between x equal to L by 4 and x equal to L by 2, we can write EI d square V by dx square equal to minus MP plus R1x minus 2P2 bracket start x minus L by 4 bracket close. And at x equal to L by 2, so moment comes out to be minus MP plus R1 L by 2 minus 2P2 into L by 4. And that gives us moment equal to 5 by 4 MP. And if we draw the bending moment diagram, the bending moment diagram is on screen in front of us. At the leftmost end, the bending moment is minus MP, and at x equal to L by 4 from the left end, the bending moment is MP, and at x equal to L by 2 from the left end, bending moment is 5 by 4 MP. Here again, we see that this beam is experiencing a bending moment greater than MP at a distance of x equal to L by 2 from the left end. So again, this solution is not the exact solution, but it does give us a good estimate. It gives us upper bound again. So the load, the plastic limit load calculated using this collapse mechanism would be more than the plastic limit load. And the plastic limit load has to be less than 3.5 MP by L, where P2 is, as suggested by this collapse mechanism, P2 is 3.5 MP by L. So the plastic limit load would be less than 3.5 MP by L. Now this motivates us to think of some other collapse mechanism. Now let us think of another collapse mechanism, and we have another collapse mechanism in front of us on the screen. In this collapse mechanism, again, there are two hinges. One hinge is at x equal to 0 at the leftmost end, the end A. And there is a hinge at x equal to L by 2 from the right end. And so two plastic hinges at x equal to 0 and at x equal to L by 2. The plastic hinge at x equal to 0 is experiencing an angular rotation of delta theta, and plastic hinge at x equal to L by 2 is experiencing a plastic rotation of 2 delta theta. Now again, let us try to find out the external virtual work, which in this case would be equal to 2p3 L delta theta by 4 plus p3 into L by 2 into delta theta. And the internal virtual work would be mp delta theta plus mp into 2 delta theta. Equating the two, we get the value of p3 as 3 mp by L. Now let us find out the reactions R5 and R6 of the free body diagram. Using the deflection equation, EI d square V by dx square equal to R5x minus MP minus 6 MP by L bracket start x minus L by 4 bracket close minus 3 MP by L bracket start x minus L by 2 bracket close. And at x equal to L, we get 0 equal to R5L minus MP minus 6 MP by L into 3L by 4 minus 3 MP by L into L by 2. And this gives us the value of R5 as 7 MP by L and R6 as 2 MP by L. Now using these reactions, R5 equal to 7 MP by L and R6 equal to 2 MP by L, and using P3 equal to 3 MP by L, let us draw the bending moment diagram corresponding to this collapse mechanism which we have proposed. If we draw the bending moment diagram now for the third collapse mechanism which we have suggested, we get bending moment at x equal to L by 4 as 3 MP by 4, and bending moment at x equal to L by 2 we get equal to MP. And the bending moment diagram is here in front of us on the screen. So at x equal to 0, the bending moment is minus MP, and at x equal to L by 2, the bending moment is MP. Now, worth appreciating here is that there is no point in the beam where bending moment is greater than the plastic bending moment MP. So this confirms the correct choice of the mechanism. So this mechanism which we have chosen for this particular beam, this collapse mechanism is perfect. And the solution which we have arrived at of the plastic limit load, the solution is exact. So you can see on the screen, I have written exact in capital because this gives us the very appropriate value of plastic limit load. Now let us look at another example which is there on our screen. This is again a beam which is fixed at the left end and simply supported at the right end, and this beam is carrying a distributed load, uniformly distributed load of W0 Newton per meter, and the reactions at the left end is RA and the reaction at the right end is RB. It's experiencing a moment MA at the left end. Let us consider a section at distance x, and we can write the deflection equation as EI d square V by dx square equal to minus MA plus RAX minus W0 x square by 2. Here we can see that the moment, the bending moment diagram for this particular beam with this particular loading would be nonlinear. The bending moment diagram would be nonlinear, it would be a curve, and it would continuously vary. It is a continuous function. Now it would not have a very distinct peak of the bending moment. Now here you can see, if you look at this bending moment diagram, there is a distinct peak. If you look at this particular bending moment diagram, again there is a distinct peak. But here the peak would be arrived at gradually. Now this is some sort of, this is the bending moment diagram corresponding to this nonlinear second order quadratic equation of the bending moment. At x equal to 0, the bending moment is minus MP, and at x equal to A, let us assume that we will develop a plastic hinge. So I'm drawing a free body diagram of the beam part equal to of length B from the right end, which is experiencing a uniformly distributing load of W, and on the left end it is experiencing a plastic moment MP. Now I have written this uniformly distributed load as WULT. So this is the plastic limit load. Here we are trying to find out what would be the plastic limit uniformly distributed load for this beam. Now if we equate bending moment at and A equal to 0, we get MP minus WULT B square by 2 equal to 0. And now let us consider the second part of the beam of length A from the left end of the beam. So this is that part, and here again on the left hand the bending moment is MP, and on the right hand again the bending moment is MP, and this is experiencing a uniformly distributed load of WULT, which is the plastic limit load, and the length of the this particular part of the beam would be L minus B. Again, we can write for this is this beam MP minus WULT bracket start L minus B bracket close whole square divided by 2 equal to minus MP. From equation 2 and equation 1, if we use these two equations simultaneously, we can find out the value of B as, we'll get a quadratic equation in B as B square plus 2LB minus L square equal to 0. And if we solve it, we get the value of B as B equal to L bracket start minus 1 plus under root 2 bracket close. And that gives us ultimate load as 2 MP by B square equal to 2 MP divided by bracket start under root 2 minus 1 into B whole square. Now the same result, let us try to find out using the principle of virtual work. Here we have assumed a collapse mechanism where there is a hinge at x equal to A from the left hand or at x equal to B from the right hand. And you can see that the plastic hinge is experiencing a vertical deflection of delta triangle equal to A delta theta. And you can see that the whole angular deformation experienced by the hinge, plastic hinge at x equal to A from the left hand would be equal to A delta theta by B plus delta theta, where delta theta is the angular rotation experienced by the hinge, the plastic hinge at the leftmost end of the beam. So the external work would be equal to WULT into L into delta triangle by 2. Now here it is worth appreciating that since it's a distributed load and the load is acting throughout the beam, the span of the beam, we have assumed the average deflection of the beam as delta triangle by 2. The load, total load has been taken as WULT into L, and the average deflection has been taken as delta triangle by 2. So that gives us external virtual work as WULT into L into A delta theta by 2. And internal virtual work would be MP delta theta plus MP bracket start 1 plus A by B bracket close delta theta. So if we use that from here, equating external virtual work equal to internal virtual work, we get WULT equal to 2 MP bracket start 2L minus A bracket close divided by L into bracket start LA minus A square bracket close. Now here we want to find out how much would be the plastic limit load. So here we need to differentiate this with respect to A. So we are differentiating this expression with respect to A, and we get dWULT by dA equal to 0. And that gives us A equal to bracket start 2 minus under root 2 bracket close into L, and B equal to bracket start under root 2 minus 1 bracket close into L. So you can see that this is the same result which we had found earlier by method of equilibrium. So B equal to bracket start under root 2 minus 1 bracket close. So this we had derived earlier, and now again we have derived using principle of virtual work, B equal to bracket start under root 2 minus 1 bracket close into capital L. Thank you.